All right, welcome back to Intro to Speech Understanding. Well, as usual, let's first go ahead and download this week's lecture. So if we go to on my computer, I have this stored under KCGI Intro Speech Understanding. And if I type LS here on a Macintosh, you can type LS. On Windows, you can type DIR. We can see that last week we finished up through lecture 7. So now if we fetch the release and then merge the release. Ah, it says I have local changes that would be overwritten. Um, let's see if I can just commit. You know what? I'm just going to remove my local copy of Lecture 7 Grade Pi because I don't know what change that is and I don't think it's important. Now let's see if I can do a git merge. I had an error because it didn't know what to do with my local copy of Lecture 7 Grade.pi, which is different apparently from the distribution version. And we have allow unrelated histories chosen, but apparently that one was not unrelated. So now that I've just deleted it, let's see if I can now merge these. There we go. And now if we list, yes, now we have lecture 8. By the way, if you ever break this, you can just create a completely new one, right? If Git ever gets so screwed up that you can't figure out how to solve it, go back to lecture 1 and just type. So let me go up here, list. Let's make dir temp, and let's go into directory temp. If you go to the temporary directory, there's nothing here. If we just do git pull jhase, let's see, what is it called? What's the original directory called? Let's see if we can just pull this. Git, not pull, we'll do git clone. If you clone it like that, oh, actually, that's probably not the best way to do it though. But that's one way to do it is to just clone the entire current directory and then go in, be sure to set the remotes so that you can check in the release correctly. I don't need all of that though. So let me actually cancel that. Instead, let me go back up to it. So basically, if Git ever gets so screwed up, then just go back to lecture 1 and use the procedure that we used in lecture 1 to clone your own personal repository, and then you should be able to start over again. But since I don't need to do that, I'm going to go ahead and go into lecture 8. And here we see we have grade.py as usual, homework 8.py, lecture 8 notebook.ipynb, and train.m4a, which is an audio waveform. I wonder if I can play that using just the play command. I'm not sure if the play command will work for that. Nope, it doesn't know how to handle that. So we're going to have to use Python. Let me go ahead and start Jupyter Notebook. So I'll type Jupyter space notebook, hit return, and it should open up the Jupyter Notebook. Here we go. We want the lecture 8 notebook. Last week, we learned how to take the Fourier transform. Remember, the week before last, we learned that sound is just samples stored on your computer. It's just a vector of numbers, an array of numbers, and you play them back at a particular sampling rate, which is a particular number of samples per second. Last week, we learned how to use the Fourier transform to find out which sine waves are present in any particular audio. And we used that last time to work with musical chords, but this week we're going to work with speech waveforms. And in order to work with speech waveforms, actually, it's very helpful to have a package called Librosa. Let me look this up. This is the package that we'll use for audio inputs and outputs for most of the rest of the semester. And the reason that we'll use it for input and output is that this Librosa load has this wonderful feature that you can change the sampling rate as you load it. First of all, it loads a huge variety of different kinds of audio files, M4A or WAVE or M3, MP3. All kinds of different audio files can be loaded using Librosa. And the other thing is that if you don't want it at sampling rate 22050, if you don't want 22,000 samples per second, you can specify the sampling rate to use when you load the file. So if you don't have Librosa installed already, you can use this line to install it. If I hit run on this bar, it will try to run pip install Librosa, and it will give me an error message. It will give me a warning if it's already installed. Oh, no, it doesn't. It just says it's already installed. So in any case, it looks like I've already installed Librosa. That's good. We can just run import Librosa just to check and make sure it works. And the key feature that we're going to use this week, Librosa has many, many features for audio analysis. The only one we're going to use this week is Librosa Load. And the nice thing about Librosa Load is that we get two things. First of all, we can load that audio file M4A, which is a highly compressed audio file format developed by the MPEG Consortium, the International Organization for Standards in Switzerland, developed this M4A format. And as you saw, Apple's built-in audio play doesn't know how to handle it. We don't even have it here anymore. Oh yeah, here I tried to do play train.m4a and it said fail format, no handler for extension M4A. So Apple's built-in play program doesn't know how to handle it, but Librosa does. Librosa will read this in just fine. The other thing that's nice about Librosa is that even though this train.m4a has 44,000 samples per second, it's a very high sampling rate file. We don't want that high a sampling rate because we don't want to use that much memory. And so instead, I'm going to specify a sampling rate of 8,000. And that way it will read the file in at 44,000 samples per second and automatically convert it to just 8,000 samples per second. And then what I'm going to do is I'm going to create a speech time axis, which will be measured in seconds. So it'll be the NumPy range from 0 up to the length of the speech file. And so that'll be integers from 0 up to the number of samples in the speech file. And then I'll divide by the number of samples per second in order to get a time axis which is in seconds. And that will allow me to use to plot the speech as a function of the time axis. When I run this, you'll see that it gives a warning message. The warning message is because Librosa tries lots and lots of different packages, lots of different libraries to try to load the audio file. And at first, it tries to use something called PySound, and that fails. But notice this is a warning message, not an error message. So this is future warning. Librosa Core Audio Load is deprecated. It will be removed as of Librosa 1.0. In fact, it has not yet been removed, so we can still use this package, Librosa Core Audio Read Load. Whatever that is, that's what Librosa falls back on. PySound file failed, and so Librosa went back to this core audio read in order to load the M4 format. And so it tries a whole bunch of different formats in order to try to get that audio format. And finally, it finds a format that works. And you can see this is what the file looks like. This is the speech file that I just loaded in. It has 5 syllables. If I run IPython display audio, I can listen to it.
A, E, U, A, O.
And you can hear that this is just a recording of my own voice saying the 5 vowels, A, E, U, A, O, with lots of space in between them. Were you able to hear that okay? I think I shared that with, let me stop sharing and try again to make sure that I'm sharing it with audio. Share sound looks like it's set up. Let me play that again just to make sure that you can hear that.
A, E, U, A, O.
So you can see that this waveform has almost 1 second of silence, And then in the succeeding 4 seconds, it has these 5 syllables, ah, e, u, a, o. And what we're going to do today, for the first time, we're really going to work with speech. We're going to try to do with the speech what we did last week with musical chords. We're going to use the Fourier transform in order to analyze which sine waves are present in each of these syllables. An interesting thing happens. You can hear that that's kind of a tone, right? That tone is actually at 125 hertz. It's very close to the A 2 octaves below middle A. You remember that the middle A on the piano, if we look up Wikipedia, A440, is the pitch standard for a standard A note. Ah, is at 440 hertz. My normal speaking voice is 2 octaves lower at about 110 hertz. Actually, I'm a little bit higher than 110. I'm closer to 125 hertz normally. And so you can tell intuitively, it should be intuitively reasonable to you that at least one of the sine waves that's present in every one of these syllables is my pitch at about 125 hertz. What's really interesting is that my pitch characterizes who I am, but it doesn't tell you anything at all about which vowel I'm saying, right? If I were speaking Chinese, then my pitch would go up for some syllables and down for other syllables. Ma, 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 right? But if I'm speaking English, my pitch only tells you basically who I am. In order to find out which vowel I spoke, we need to do a bit more analysis. And so what we're going to do is we're going to do Fourier transform, but we're going to do it on a short time. And the problem with the Fourier transform, I wonder if I can zoom in on this. Yes, a little bit. Good. The problem with the Fourier transform is that it finds out which tones are present in a sound, right? But speech changes over time. So if I do a Fourier transform of this entire file, it's not going to tell me which sine waves are present in the ah. It's going to tell me which sine waves are present overall, including ah, e, u, a, o. And that's not very useful if I want to be able to tell the difference between ah, e, u, a, o. So in order to be able to tell the difference, I have to analyze these separately. And the way that we can do this is by taking the short time Fourier transform. A short time Fourier transform like this is a plot where frequency is on the y-axis, time is on the x-axis, and loudness or energy shows up as bright colors. So what's shown here is a spectrogram, which is a log magnitude short time Fourier transform. The normally used to calculate spectrograms. So here's lots of different spectrograms. Here's the one that we just saw, and here's another spectrogram, and here are many more spectrograms. Here's a spectrogram of a wavy sound, ah, like a siren. Here's a spectrogram of a more complicated sound. There's spectrograms of many different examples of spectrograms on the Wikipedia page. Let's create our own. A spectrogram is a log magnitude short time Fourier transform. So that has several pieces, and we can work sort of from the inside out. Log magnitude short time Fourier transform. All right, the short time Fourier transform means that first of all, we chop the signal up into frames. So we enframe it. That means that we take some short segment, much shorter than a vowel, usually more like 2 pitch periods. So usually like maybe 25 milliseconds. Take 25 milliseconds from the very beginning of this vowel, and then from the middle, and then from the middle, and then from the end, usually overlapping windows, and put one of those windows into each column of the matrix. Actually, each row. We're going to put one into each row. We could do columns, but this week we're going to do rows. It really doesn't matter. You can do either rows or columns, but this week let's do rows because that's easier in Python. So we'll enframe the speech. We'll just chop it up into overlapping frames and put each frame into one row of a matrix. And then we'll take the Fourier transform of each row. So this is where we do, just like last week, we check to see what sine waves are present in each 25 millisecond frame of the audio. And in that way, we can find out which sine waves are present in the ah, which sine waves are present in the e, which ones are present in the oo, and so on, right? So we can go through and check for every single one of those vowels, what are the tones that are present? Now you remember that the Fourier transform has two problems. One, it's complex valued, right? It's part imaginary. And so the first thing we have to do is calculate its absolute value. This is called absolute value and magnitude are the same thing. We'll take the magnitude, which is a synonym for the absolute value. And then after we take the absolute value, then the next problem is that audio has a very wide dynamic range. The quietest sound that you can hear is 1,000,000 times quieter than the loudest sound that you can hear. And so in order to be able to show both loud and quiet sounds, we compute the logarithm. We'll compute the logarithm over a range of 1,000,000, 10 to the sixth, which is 60 decibels. Actually, no, that's over a range of 1,000 in power. And then after we, in amplitude, then after we compute the logarithm, then we'll clip the values that are too small. We will keep only the values that are in the top range of 1,000 in amplitude, range of 1,000,000 in power. All right, so let's do each of these things in turn. We're going to chop it into frames, take the Fourier transform, take its absolute value, take the logarithm, and then clip it. So first, let's divide the speech into overlapping frames. We'll divide it into frames that are, say, 20 milliseconds long, so 0.025 times the sampling rate. And we'll skip just 10 milliseconds between the start of frames, so just 0.01 times the sampling rate. That means that the frames will overlap by n minus s samples, right? So if I can add some comments here, fs in our case is equal to 8,000 samples per second. So each frame is 0.025 times fs, which is equal to, let's see, what is 25 thousandths of 8,000? 25 times 8 is 200 samples. And we skip 0.01 times fs, which is equal to 80 samples between start of adjacent frames. And that means that the frames overlap by n minus s, which is equal to 120 samples. So neighboring frames will overlap by 120 samples. Right? So we will calculate n, which is going to be 200. S is going to be 80 samples. And then we'll do something like this. There are many ways to do this, but this is one of the easiest. We'll use the range operator in Python to start at sample number 0 and then skip by 80 samples in between. So it'll be 0 and then 80 and then 160 and then 240 and then 320. And we'll go until we get to the length of the speech file minus n, right? So we'll go until we're n samples before the end of the file. And for each of these little m start times, we'll take just this many samples. We'll take capital N samples, starting at sample number m up to sample number m plus n minus 1, right? And we'll put that into, we'll take that array, and then we'll create a list of those arrays. What this does is it creates a list of those vectors. So there will be several hundred of these vectors. Each one is exactly 200 samples long. And then we use the np.array operator to turn that list into a matrix. What it will do is take each of those subarrays and make it a row of the matrix. So the result will be 537 by 200. If I run this, I get the code at the bottom. The speech waveform is 43,000 samples long. And if we have 80 samples between the start of each frame, then that's 537 frames. Right, so it's 537 plus 80, and then plus the 200 samples for the very last frame. The shape of the resulting speech frames matrix, this speech frames dot shape, that's a matrix with 537 rows. Each row has 200 columns. All right, so now we have this speech frames, we have that arranged in a matrix. Let's actually plot it. Let's just create a figure and plot it. So if I plot that, on the x-axis, I have the frame number from 0 to 536. On the y-axis, I have the sample number within each frame from 0 to 199. And the interesting thing is that you can see the overlap between the frames shows up as this banded structure. The peaks that you see here, the bright spots that you see here, those are the peaks in this waveform. Actually, let me zoom. I can't really zoom that in. But you see that this waveform has several peaks. Every time this waveform has a peak, that peak shows up as a bright spot in this matrix. And those bright spots get shifted from one row to the next because every row is overlapped by 120 samples with the row before it. And so you can see this periodic structure during the vowel where the pitch period is 125 hertz, the pitch frequency, and we have this sort of banded structure where the waveforms are. That shows us some information about the vowel, but it's still hard to understand that information. And so in order to get it a little bit more comprehensible, we want to take the Fourier transform. So we'll take the FFT of every frame in order to get the magnitude short time Fourier transform. We'll use NumPy's FFT, which does exactly what we did last lecture, right? It takes every row of that matrix. The row is axis 1. So we'll take the FFT only along the rows. It takes every row of that matrix and multiplies it by a Fourier transform matrix so that it splits it up into frequencies. So when we plot that, here are the frequencies on the y-axis, and here are the frame numbers on the x-axis. Now I want to do three things with this. First of all, these high frequencies, you can see that these are just mirror images of the low frequencies, and that's because they're just aliased copies, right? This goes from 0 to 8,000 hertz, but above 4,000 hertz, it's just aliasing. This thing up here at 6,000 hertz is just exactly the same thing that occurred at 2,000 hertz. So I'm only going to plot the first 100 bins. I don't need to plot all 200 of them. The other two things I'm going to do are to change the frequency axis. So instead of going from 0 to 100, it goes from 0 to 4,000 hertz, right? I know that this entire range is 8,000 hertz. And so I want to convert it from FFT bins in K to frequencies in hertz. Remember, the formula from last time was we multiply by the sampling frequency Fs divided by the length of the FFT, and then multiply that ratio times K in order to get the frequency in hertz. Similarly, we can change the time axis, right? Each one of these frames starts S samples later. So in samples, the start index of the mth frame is m times S. In seconds, it's m times S over Fs. So if I take the sample index m, where the mth frame, multiply by S over Fs, I get the starting time of the frame in seconds. So I can take m is NumPy range from 0 to 537, and I can multiply it times S over Fs in order to get the x ticks. And I'll set once every m samples. Let's say that I take every 100 samples, I'll create an m-axis. Once every 100 samples, I'll label the axis with the corresponding time in seconds. Similarly, once every 25 FFT bins, I will label with the corresponding frequency in hertz. And if I run that code, then I get a plot not of the entire spectrogram, but just from 0 to 100, just the low half. And here are the low half frequencies from 0 to 4,000 hertz. And here's the time. You see, just like the original audio file, we can check to make sure the original audio file was 5 seconds long. And so we can check and make sure that we got our time scaling correct. The time scaling here says that the time in seconds is just over 5 seconds. And we can see now, ah, E, U, A, O. That information is now, we can now easily see where each of the syllables is. We can also easily see that there's a bright horizontal bar at 125 hertz, right? That's about 1/8 of 1,000. So we have 0 to 1,000 is here. We have about 8 lines. And so there's a bright horizontal bar at 125 hertz. My pitch frequency, that pitch frequency at 125 hertz, shows up as a bright bar. There's another bright bar here at about 250. And after that, it's really hard to see what's going on. The reason it's really hard to see what's going on is that your ear is much more sensitive than your eye. The brightest pixel that your eye can see is only about 250 times as bright as the dimmest pixel. The loudest sound that your ear can hear is 1 million times as loud as the quietest sound, just in terms of signal amplitude. You take the amplitude of the quietest sound you can hear and multiply it by 1 million, you get the loudest sound you can hear. In this case, by loud, I'm talking about like jet engine loud, rock concert loud, right? 1 million, you take the very quietest sound that you can hear in a quiet room, multiply its amplitude by 1 million, and you get a jet engine. So that's a huge range, right? That's much, much more than the range of sound is much, much more than the range of vision. And so, in order to take that huge range of audible sounds and compress it down to something you can meaningfully see, we need to use a compressive nonlinearity, something like a logarithm. Let's see, let's go to Wikipedia logarithm to see how logarithms work. A logarithm works like this. It's a compressive nonlinearity, which means that very loud x's, very large x's, still cause the y-axis to go up a little bit, but not very much, right? So what the logarithm of x does, the logarithm takes very small x's and spreads them out, and it takes very large x's and compresses them together. And so it's a good model of our perception of loudness. In fact, your perception of loudness is pretty close to the logarithm of the amplitude of the signal. And in fact, there's a standard scale called the sound pressure level. This is, again, an international standard, standardized by the International Standards Organization. If we go here to sound pressure level, sound pressure level is a standard measure. It's 20 times the log base 10 of the pressure in decibels, the pressure relative to some reference pressure. And this is defined by ANSI standard S.1.2013. That's the standard by the American National Standards Institute. It's also a standard by the IEC, which is the International Electrotechnical Commission. So this decibels, this idea of decibels, is an international standard that's useful for measuring things like sound pressure level and many other kinds of power measurements. Electrical power is also often measured with decibels. If you've ever worked with a mixing board, like if you've done DJing or anything like that, or sound mixing, you've worked with decibels. You know that it's pretty close to measuring what the loudness that humans hear. It's not quite exactly the same as loudness, but it's quite close. And so we'll use this standard. We'll take the magnitude short time Fourier transform, we'll take its log base 10 using the log 10 command, and then we'll multiply that by 20 in order to get decibels. The other thing we'll do is that the problem with logarithm, if we go back to logarithm, the problem with logarithm is that values that get close to 0 have a logarithm of minus infinity. And that's just not useful. We're interested in small values, but we're not interested in values that are very, very small. And so what we'll just go ahead and clip it to 1/1000th of the maximum. So whatever the maximum amplitude is, we will only go down 60 decibels, right? 20 times the log base 10 of the log base 10 of 0.001 is -3, right? This is 10 to the minus third. And so when we take the log base 10 of that, it'll be -3. We take 20 times -3, it'll be -60. So whatever is the maximum value of the matrix, we'll take maximum in order to clip the decibels to no less than 60 decibels below that. So here's how that works. We take the magnitude short time Fourier transform, and then we find its maximum value, and then we take 0.001 times that maximum value, and then we use the np.maximum command. What this does is anytime that MSTFT falls below 0.001 times its maximum, it replaces it with 0.001 times its maximum. Once we've clipped it in that way, then we can just take 20 times the log base 10. And the rest of this is just plotting it with an x-axis in seconds and a y-axis in hertz. And you can see now, like with the MSTFT, we could see that there were 5 syllables, but we couldn't see much information. In decibels, we can see a lot of information. Look, you can see the bright line at 125 hertz and then another at 250 hertz. You can see that the ah and the e are very different because the ah has a lot of energy here at around 1,000 hertz. The e has a lot of energy up here between 2,000 and 3,000 hertz, right? The oo has energy much more distributed, basically at 0, 1,000, and 2,000. The a is like the e, but not quite as high. And the o is like the oo, except even lower, right? The O is, doesn't have very much at 2,000. It's mostly here between 0 and 1,000. And so by doing these 5 steps of the spectrogram and framing, Fourier transform, absolute value, logarithm, and then clipping, we get an image that allows us to tell the difference between the different vowels. This is called a spectrogram. This is the starting of how to analyze speech. If you want to analyze speech, this is the representation that everybody uses. Everybody who studies speech will use this representation called the spectrogram. Let's talk a little bit about these horizontal lines. These horizontal lines tell us the pitch, right? I told you that this is, I'm speaking at a pitch of about 125 hertz. That's the A note, which is 2 octaves below middle A, right? And so this most obvious feature, unfortunately, has nothing to do with the vowel. What we would really like to do is to smooth out these horizontal bars, smooth them out, and instead just emphasize the differences between the vowels. So if you look closely, you can see that the ah has energy at about 900 and 1100 and 2500 hertz, right? Here at about 900, here at about 1100, here at about 2500. And the E has lots of extra energy down here at around 250, and then its next energy is up here above 2000 and at about 2500. The U has lots of energy at 250, and then again at 1,000, and then again at 2,000. The A is more like an E. It has lots of energy, but maybe a little higher at 400, and then at 2,000 and 2,500. The O is like an U, but even lower. It has lots of energy at 400, and then at maybe 900, maybe a little bit below this 1,000. Right? So we can scale it like this. We can say that here's my measurements of those 3 formant frequencies for each of the vowels. This is the kind of information that we want for automatic speech recognition. We want to be able to tell the difference between these different vowels by looking to see what are these formant frequencies? What are the differences in the spectral shape between these vowels? And in order to emphasize that, we can do something called a wideband spectrogram. A wideband spectrogram hides the pitch by using very short windows. And the trick is this. So far, we used a window which was 25 milliseconds long, but my pitch is 125 hertz. 1 over 125 is 0.08 seconds. Is 8 milliseconds, right? So if the window is longer than 1 pitch period, then the spectrogram is going to show these horizontal bars that represent my pitch frequency. But if the window is less than 8 milliseconds long, then the spectrogram will no longer show these horizontal bars. Instead, it will just show the rough shape. So this is the key difference. A narrowband spectrogram uses a long window, longer than 1 pitch period, and a wideband spectrogram uses a short window, shorter than 1 pitch period. So for example, if we want a wideband spectrogram, we can use a window which is only 4 milliseconds long, 0.004 times fs. So let me write this in. The sampling rate is fs equals 8,000 hertz, samples per second, I guess I should say. So for a wideband spectrogram, the pitch is 125 hertz, which is a period of 1 over 125 equals 0.008 seconds, 8 milliseconds. So a wideband spectrogram can be achieved using any window which is shorter than 8 milliseconds, but just to be safe, let's make it 1/2 of a pitch period. So we'll make it 4 milliseconds long times fs, you remember, is 8,000 samples per second. So 4 times 8 is just 32 samples. The Fourier transform now will just be 32 samples long. The step size, we'll make the step size half of that in order to make sure that the windows overlap. 0.002 seconds times 8,000 samples per second. So the step size in between windows will just be 16 samples. And then the overlap is n minus s, which is 16 samples. So we'll use 32 sample windows overlapping by 16 samples. That's obviously very short. So this n is going to come out to be 32 samples. This s will come out to be 16 samples. And then we'll create a set of frames the same way that we did before. We'll create a magnitude short time Fourier transform, and then we'll take its 20 times the log base 10 in order to calculate the spectrogram, and we'll plot it again. And the result, now you can see that the horizontal bars for the pitch are gone, right? These horizontal bars for the pitch are gone. And instead, all we have is energy representing the vowel. We still have a lot of energy at low frequency for the ah, but you can see lots of energy at 900 and 1100. For the e, you can see this energy at around 250, this strong bar at 250, and then something at 2500. Well, there's still just too much energy at low frequencies here. So there's one more trick we can try. This one additional trick is something called preemphasis. So notice that even though the pitch harmonics aren't visible anymore, there still seems to be most of the energy is down here at the very low frequencies. And we can get rid of that low frequency energy by analyzing the difference between neighboring samples instead of analyzing the sample. This is a very, very old and very cheap trick, right? It's a cheap trick for getting rid of the low frequency energy. If you just don't want that low frequency energy there, you just get rid of it by subtracting neighboring samples. So preemphasis means that I just take the speech frame from m plus 1 to m plus 1 plus n minus the speech frame from m to m plus n, right? And by analyzing that difference instead of x of n, I can just get rid of the low frequency energy while keeping all of the other energy. So if I run that, you see that we have, here's the preemphasized spectrogram. Notice that it's just like this spectrogram, except that all of the very low frequency energy at 120 hertz is gone. And so the ah, right, the ah doesn't have any low frequency energy anymore, but the e does, right? You couldn't really see that difference obviously here. There's some energy at low frequency here, and here there's energy at low frequency, but a little bit higher. That's important. This low frequency energy is just pitch, whereas this low frequency energy tells you something about the vowel. And the reason is that this low frequency energy is at 250 hertz, and this low frequency is just my pitch, 125. And by pre-emphasizing, we get rid of that. Now we can really see that the ah has energy at 900 and 1100, the e has energy at 250, 2000, and 3500. The U has energy at 250 and 1000. The A has energy at 400 and 2000. The O has energy at 400 and 1000, right? So it's just like 250 and 2000, 250 and 1000, 400 and 2000, 400 and 1000. That's the difference between E, U, A, and O. It's really that simple. And then awe is the weird one. Awe has energy at just below 1,000 and just above 1,000. All right, we'll come back and talk a lot more about the difference between vowels over the next few lectures. But for the homework this week, we're just going to work on the spectrogram. Let's open up the homework file. Homework 8.py will have three different functions, one that converts the waveform into frames, one that converts the frames into the magnitude short time Fourier transform, and one that converts the magnitude short time Fourier transform into a spectrogram. All right, so if we look at that, let's see what this takes in a waveform and a frame length and a step, and it should create as output a matrix whose size is the number of frames. The number of rows is equal to the number of frames, and the number of columns is equal to the number of samples per frame. There we go. We don't want the runtime error. Instead, what we want is we want to return a NumPy array, which is created as a list, and the list is waveform from m to m plus n for m in the range between starting at 0 and going to the length of the waveform minus n and ending with and stepping with every step size. And I used n here, but that's not right because in the parameter it's specified as frame length. So it's the length of the waveform minus the frame length. And this n also should be the frame length. And that should do it. That creates a list of NumPy arrays, each frame length long, and each separated by one step. And then it turns that list into a matrix. Let me save this and see if that works in the code, in the sample code. So here I'm going to import homework 8 and then run the help file. And then here I'm going to run its waveforms to frame file and plot the result. And here's the result. Notice I have to transpose it so that it puts the row index on the x-axis and the column index on the y-axis. And there's the frames of the speech. The second function for the homework converts the frames to the magnitude short time Fourier transform. So this takes in a frames matrix and outputs an MSTFT matrix. So again, this just means that we take the FFT, we'll take NumPy FFT of frames, and we want to make sure that we take the FFT along the row axis, and then we want to take the absolute value of the result. And then the absolute value of the result is what we return. So this will return the absolute value of the FFT of the frames, FFT only along the row axis. Let me save that file and let's run it in the test code and see if that works. So when we run the help on that, we get the help function. And let me try running frames to MSTFT, and now that works and it creates the magnitude short time Fourier transform, A, E, U, A, O. All right, and then finally, we want to convert that to a spectrogram. MST to spectrogram takes, first of all, the maximum of MSTFT or 1/1000th of its maximum value, right? So this is just taking every value of MSTFT that's lower than this threshold and clipping it to that threshold. So it never gets too large. And we do that using, you remember, numpy.maximum of 0.001 times numpy.amax of MSTFT. The amax finds the maximum value over the whole matrix, and then maximum does an element-wise maximum. It says every element of MSTFT, if it's less than this threshold, replace it by that threshold. All right, now that we've done that, now we want to return the spectrogram, which is just 20 times the log base 10 of that result. So we want to return 20 times the log base 10 of the maximum of 1/1000th of the Amax or the MSTFT. So that should compute the whole spectrogram. Let's save that and let's test it with the Jupyter Notebook. We test that with the Jupyter Notebook. There we have our spectrogram: A, E, U, A, and O. Let's just test our code using the auto grader here. Let's run the grading code and make sure that it works. ran 3 tests in 0.024 seconds, and 3 tests again in 0.017 seconds, score 100%. Excellent. So if the score is 100%, now we should be able to check it in. Let me go ahead and start GitHub Desktop. And here's all the things I changed. That looks pretty good. So let's say homework 8. I did homework 8, and we'll commit it to main and push it to origin. And then go to your own intro speech understanding. This is my teacher account. I don't want my teacher account. I want my student account. So go to my student account and make sure that in my student account, lecture 8 has homework 8 completed. And there I have NumPy array of the frames. Here I have the absolute value of the FFT. And here I have the logarithm of the maximum. So all of that is correct. I'll go to the copy the URL, and then go to homework 8. And then I should be able to just submit it, enter the URL of your copy of homework8.py here. And once you do that, you should be able to submit the homework, and you should be able to see the result. I will then go through and check the results, and you should be able to get the grade back. All right, that's all we have for today. Let me end the recording.